So I'm going to present a bit of an overview about what we do in the area of 3D printing of sensors. Bit of overview of the group at Warwick. So we're not necessarily a sensors group. We're an additive manufacturing 3D printing group. So we do things all the way from biodegradable scaffolds all the way through up to aerospace components and pretty much everything in between. And we approach that from three kind of areas. So it's designing the materials and formulating materials, building systems and machines, and actually doing the applications. And for that end, I employ chemists. I've got an electronics engineer, mechatronics engineer, and chemical engineer, because it takes all those skills to bring together into this area. A little bit about our facilities. This doesn't make any sense to you. I do apologise. So hopefully it will make sense as we go through. So the biggest thing we do is stereolithography, so resin-based 3D printing. And we use commercial systems. We build a hell of a lot of our own as well to control the parameters. Lots of fused deposition modelling, which is a thermoplastic 3D printing. Again, lots of custom-built systems. We've just got a 3D platform, which is a metre by a metre by half metre print bed to do really large parts. Domatics inkjet, so we do print electronics type stuff as well. And then our own CT system and material development lab. So a full range of stuff in the polymer side anyway. Overview about what I'll talk about is what is 3D printing, just a quick introduction. I know you had an introduction earlier in the conference. The technologies, why 3D print the sensor, and the work we've done on 3D printing sensors. I'll skip through that one. For those of you not familiar with 3D printing, that's the technical definition, the process of joining materials to make objects from a 3D model layer, usually layer by layer, blah, blah, blah. I like to think of it as combining art, science, technology, engineering to create a real-world object, essentially. Just to define what I'm talking about, so 3D means lots of different things to lots of different people. If you're an inkjet person, 3D is a couple of layers thick. If you're a kind of nano surface person, 3D is a couple of nanoparticles stacked on top of each other. What we're talking about here is taking a CAD design, send it to a system which renders that layer by layer to build up a 3D object. The technologies, obviously the technology itself has been around for 20-25 years. It's grown though to a huge amount of processes which fall under this 3D printing additive manufacturing label. So all the way from metal, so electron beam melting, selective laser melting, through to the polymer and plastic stuff, so FDM, SLA, and then all sorts of things like concrete and bioplotting and foodstuff printing, and pretty much everything in between. Usually these days, if you think of the material, someone's tried to print it somewhere. The things we deal with most really are FDM and stereolithography. FDM is the process that kind of is behind all the very cheap desktop printers that you see. And it's taking a thermoplastic feedstock or another material feedstock, send it through what's essentially a glorified hot glue gun to melt it or to extrude it, and then to do that in a 3D shape. Sometimes in a multi-material fashion. And so using things like thermoplastics, liquids, gels, ceramics, concrete. Just demonstrating the process, you kind of get the idea. It took me ages in PowerPoint. Stereolithography, on the other hand, is one of the oldest forms of technology. So using a photopolymerizable resin, then taking your 3D CAD file, turn it into in this case, because it's a projection system, a number of images which you then project onto this layer of resin that's sandwiched between a build plate and this almost like silicone layer. Then you use the light from the projector to solidify the resin and just keep doing that over and over again. You can also use a laser to run over the surface, and there are benefits to that and also downsides. Any of you that are really into technology will know about carbon 3D technology and the continuous process as well. This carbon 3D stuff, I think it's just 7 times faster it's meant to be. So actually, the traditional form of this is you do a polymerization, you stop, you move up, more material flows in, you keep doing that. Whereas carbon are actually doing a full continuous extrusion, so they don't do any pauses in their prints. Again, there are benefits and downsides to that as well. So, guess why we're here? Why 3D print a sensor? You kind of all know what a sensor is. I don't need to give you well, hopefully you know what a sensor is. I don't need to give you the definition. There are many types. So acoustic sensors, chemical sensors, optical sensors, pressure sensors, force sensors, there's a whole range. And what we're trying to do in this kind of area is build ourselves a toolkit of being able to make all these sensors via a 3D printing process. And that's not because we want to 3D print everything, it's just, so if people come to me and say, why do you want, or can I 3D print this? My first response to them is, why do you want to 3D print it? If there's a more appropriate technology, please do use that technology. So when people come to me and say, I want to 3D print a circuit board, you say, why do you want to 3D print a circuit board? A circuit board can easily be made by another existing process. You don't want to reinvent the wheel. Actually, if you're trying to do things like circuits with them, you'd look at trying to put circuits where you wouldn't normally find circuits. And that's the real power of technology. At the moment for sensors, if you want to buy a sensor, generally, if you've not got the capability to make one, you'll look up in a catalogue and try and find one that just about fits for your application. Whereas because you've got this on-demand type process for 3D printing, maybe we can make it much more bespoke for your particular application. I guess you're fairly familiar with how sensors are made commercially at the moment. So what can 3D printing offer us? Well, small-scale production runs. You don't need a whole factory to make your sensor. Rapid turnaround. So my students can make a sensor every 20, 30 minutes in a completely new design. So if we're doing kind of R&D sensor work or doing bespoke stuff, actually gives you much more rapid turnaround than trying to do it by a conventional process. And there's a business case element to that. So yes, if you want to make 1 million of them, this probably wouldn't be the process you'd use. Improved time to market. Again, if you're doing small volumes of these things. And new shapes, so mission-specific sensors. So can we make things that are optimized for the particular application where you want to put them? They're designed or optimized for that job. And new locations. So this goes back to the why you want to 3D print stuff. So can we put a sensor where you wouldn't necessarily normally find a sensor, or there isn't a traditional process that you could use to do that? And that comes hand in hand then with embedding. So can we embed sensors in objects and make them much smarter? Our approach is not rapid prototyping. We're not looking to just make a box to put our sensors in. That just doesn't really float my boat. To do what we want to do, we explore the outset using simple functional materials. So this is very basic composites where we take a functional material, embed that in a composite and use that function to a sensing capability. As I said, we're not trying to replace conventional processes. We're trying to give a new process or something else in the toolbox or the armory of processes. So some of the things I'll go through that we've done. 3D printing flow sensors. 3D printing replacement flow sensors. You'll see the difference when I get to it. Flex sensors. Interface devices and sensors. Embedding sensors using 3D printing. Gas and vapor sensors. This is fairly new to us as well. And ultrasonic piezometers as well that we've done. So there's a fairly broad range of what we've done there. So the first off, the flow sensor. This is work we started back in 2011. So this is using our SLA process, so the resin-based photopolymerizal process. So it's a 3D lithography. Taking our polymer resin, this is a custom formulation of our polymer resin, and just putting carbon black particles, sorry, not carbon black particles, magnetite particles in this one. So just putting very simple off-the-shelf magnetite particles in the resin, and using our process as a bit of a reactor to embed these in the solid composite. So taking our polymer formulation, putting in our magnetite particles, creating our cross-linked nanocomposite, and using it, in this case, to print impellers. So impellers are flow sensors. The idea is you print out your flow sensor body, you then print out your impeller inside with magnetite nanoparticles in. Then when you flow air or liquid through this, you get to see the rotation of the impeller using, in this case, it was an AMR sensor, magneto-resistant sensor. So it's how flow sensors are conventionally made, but it's actually being able to do it bespoke. So if you wanted to change this manifold, we'd put this one in the bin, or the recycling bin, and print out another one in the 20 minutes and have a different sensor. And then we get the output from this, so again, different shape sensor. But using that, and then I think this is hooked up to an airline, varying the pressure of the airline, you can see the rotations change and use it as a sensor. Incorporate it into things like microfluidic devices, so we get a nice linear response from this. So again, another variation of this process. and nice and repeatable as well. So 3 different runs, nice overlapping data, really nice sensing mechanism. And we can start incorporating this into different structures, so lab-on-chip devices, maybe it's things like wearable devices, etc. So a nice little demonstrator. Possible future applications, I'll do this at the end of each sensor I go through, just to give an overview. So we can start thinking about bespoke medical devices, lab-on-demand type applications. This is a sensor or a system we've just recently produced, so I don't know if you can see it from the back. We've got a mechanical filter here, so various different size posts in the chip device. One of our flow sensors, a separation channel, and also 3D printed electrodes, all done with SLA in 2 builds. So a nice, highly functional device made in about, say, half an hour. Some more flow sensors. This is using, this time, FDM, so a thermoplastic technology. Again, magnetite nanoparticles embedded in a thermoplastic this time. Conventional commercial sensor uses a Hall effect sensor to sense the rotation of a entirely kind of ferrous impeller. We copied this design, or imitated this design, made our own impeller. Rather than use make the whole of the impeller like from the magnetite material, we just did 2 layers, so about 200 microns on top. So the rest was thermoplastic and then just 2 layers of this functional material. So you can see the layers on top of the impeller. So fairly simple device. To make the functional material wasn't particularly high tech. It was solution dispersion of the magnetite particles in the polymer matrix. This is just an X-ray image to show the dispersion of the particles through the impeller. A graph here showing the correlation between our printed flow sensor and the commercial flow sensor, so get fairly good agreement. The graph on the right shows just an enclosed or a completely closed loop water-based system with varying pump voltage to increase the flow. A nice linear one at the bottom is actually our printed one, it's not the commercial one. So it's actually in this case behaving better than the commercial sensor for this application. And that's then counterintuitive to people's perception of 3D printing technologies. So everyone perceives that the objects you get at the end are not necessarily as good as a conventional object. It's telling you different. Whether it would last as long is a different matter. But if you actually want to make one quite rapidly for kind of rapid replacement, then this is a viable process. So applications, things like localized manufacturing, rapid replacement of infrastructure, maybe replacing legacy systems, so making bits to fit into legacy systems where we can't get the parts anymore. It's all on the table thanks to this kind of technology. 3D printed flex sensors, so sticking with the FDM or the thermoplastic technology. This time using carbon black embedded in a thermoplastic matrix. Again, solution dispersion. In this case, the filament, so the filament we feed into the system was actually rolled by hand. So there's no compounding, it was entirely solution dispersed, solvent evaporated, and essentially just rolling about a meter's worth of filament by hand. It was enough to get us test filament to run through the process. So it's not, so the barrier to entry in doing this stuff is not massive. You don't need a full kind of compounding and master batch system. You can make small lengths of it really easily by this kind of process. This application was making flex sensors, so taking an existing bit of plastic sheet, printing directly onto that plastic sheet, essentially a very small track. For those who deal with things like print electronics conventionally, you know that you do your kind of serpentine, your strain gauge, you've still got to interface to it somehow, and that's via conductive epoxy or conductive paint. In this case, we just printed 2 sockets, plugged into kind of crocodile, like banana plugs, and just got a working sensor straight away. So again, that was in about 20 minutes, half an hour. We had a sensor on an existing bit of existing material that we just plugged straight into. So it got over the things like contact resistance and stuff. Potential applications for this, adding sensors to aging infrastructure, tailoring sensors to the shape of objects. Obviously the world around us is changing, the way we build buildings is changing, therefore we need much more tailored sensors. Anyone familiar with kind of the CAD and 3D design area will know about things like generative design. So being able to put sensors on objects which then feed back to the original design process. It's almost making a kind of nervous system for an object. So all again, this is opened up by this kind of process. Using the same material, but in this case to make interface devices. So this is a single print build. So it's 2 material, single print build, probably 25 minutes, half an hour. So using the green material is just an ABS, the black material is our carbon-loaded thermoplastic. Depositing that, again, banana plug straight in the back, and using it as an interface device and looking at the capacitance change when you touch it. The bit at the bottom is a nice little demonstrator of what we did with that. So we made a small length of this filament, about this long, sent it to a school down in Bristol in the UK, a teacher who was very into product design. And knowing what this material did, these school kids designed this stylus for an iPad. So it's normal kind of thermoplastic, but with our thermoplastic printed straight in the center of it, so we can use it as a stylus. And they had probably 2 foot material that allowed them to do the whole concept, product design and manufacture process in a day in a school, just because they had this simple functional material. We released the process to this via a +1 paper, so it was an open access paper, and a lot of people have done kind of stuff since that. The kind of picture that will come up if you do a search for this is our games controller. So again, this was a single process print. You take it off, you put your 6 wires in the back, and you've got a kind of bespoke interface device. Maybe it's because someone with reduced mobility will need an interface device in a particular way. Then again, this is opened up by this process. That part is now in the British Science Museum in their permanent collection as well. So they featured that in an exhibit when it came out, and it's now in their permanent collection. Possible applications, so bespoke user interfaces, bespoke hardware in the future. I guess you've all seen this idea of kind of bespoke mobile phones. Some of these products have obviously been canned, but this idea to making something more tailored to you and that you'll keep it for longer, etc. Embedded sensors, so same material, printed like an exo glove with this. Again, single print process. So using two materials, some very small strips of this process, just in this material in the finger, and again using that as an interface device. Really quick print, nice interface device straight off the machine. Sensors in new places, again, a multi-material print, but this case putting the material inside a smart vessel. So using this capacitive sensor to detect how much liquid is in this vessel. If you looked at objects afterwards, you wouldn't know the sensor was there inside it. And this is the idea of trying to put electronics where you wouldn't necessarily find them conventionally. Quite a way you want to know how much coffee is left in your coffee cup, because you can do that visually, but it's just a nice demonstrator of what we're trying to do. And so you can think of things like hidden security, Internet of Things. This thing we're really getting into now is physical sentiment analysis. I'll let you fill in where that potentially you could think that could go. That's a live project for us at the moment. Vapor sensors, so this is something fairly new to us as well. So we live next door to a gas sensors group. And in terms of a vapor sensor or gas sensor, it's not particularly complex. This is done via SLA, so putting carbon particles in a swellable polymer matrix. Printing this with a substrate as well. Changing the structure. Obviously, as you flow gas or vapor over it, the polymer expands and you change the resistance. So we get nice responses to things like toluene. Got all the data for different relative humidities. We see geometry-dependent behavior, so we can change the geometry of the gas sensor and change its response. The thing to take away from this is we are changing the structure and we're still seeing a response, which is quite nice. So actually we can start thinking about putting environmental sensors within a 3D printed object because we're doing this. So things like embedded structural sensors, embedded environmental monitoring, again, all opened up because we've got this toolkit of processes. And kind of one of the most recent things as well is looking at making ultrasonic transducers, so making mission-specific transducers. So using our SLA process again, this time put in PMNT ceramic particles in our resin. We then do our print process. I should start with C actually. You get this nice green body, so this composite at the end of it, which is our ceramic particles embedded in our polymer matrix. That's the SCM of the nice well-dispersed particles there. That is about 3 months' work to get to that point, to get the resin behaving quite nicely so that it's fully dispersed. But to start, you think it's going to be easy, just put particles in a polymer matrix. You get nice kind of resin-rich areas and particle-rich areas. So that takes an awful lot of work to get to that point. You then do the firing, so yes, you get some shrinkage, but it's nice and uniform. You get nice kind of dense ceramics. You don't really see any effects of a layering apart from this kind of sub 100 micron indent occasionally. You get a nice dense ceramic at the end of it. And again, there's a perception that 3D printed objects are not as good as the real thing. The density of this 3D printed ceramic after firing is indistinguishable from conventionally produced ceramic. D33, so its piezoelectric coefficient, is identical from conventionally produced ceramic, but we've got control over the structure, which you can't necessarily get easily with a conventional ceramic process. So we can make piezo arrays, we can make curved piezo arrays, we can change the shape of the pillars in piezo arrays as well, and change like the cross-coupling behaviour. Can't really see the graph at the end there, but it's basically showing there's very little cross-coupling between those. So it's as good as conventional process, but we've got much more control over the structure. People who deal with things like piezos and ultrasound, this air measurement shouldn't really be very easy. Because of something I won't necessarily go into because of trying to commercialize it, these work great as air-coupled transducers. We are also thinking of, well, we have done printing of things like matching layers as well for piezos, so we can print those directly in the process and onto piezos afterwards. But these couple really well into air. And you can see as we change the receiver distance, we get a change in the response. So again, a nice little demonstration of where the process is at the moment. And again, things like control over the structure. So changing the shapes of arrays, pillars that change or spin in cross sections as we go up, these are all opened up by this process. And then nice kind of demonstration. So almost taking the pasta shape approach, so trying different shapes of ceramic and seeing what we can do. Anyone familiar with things which live, or vessels which live underwater, will know why kind of circular structures are great in piezos. If we demonstrated we can do that on our SLA process and map the field coming out of them. So things like, we can think of things like bespoke medical imaging, energy harvesting, embedded energy harvesting. Again, all these are opened up by this tool, this process. So that's a fairly brief and quick review of what we've done in this area. As I say, it's not necessarily our main body of focus, but we've done a fair bit in making sensors via 3D processes. And we're still going in this area. Looking forward, again, these are all live projects. So hybridization in manufacturing processes. Can we add sensors to existing 3D objects via a 3D process? That's just a bone structure there. We've added a strain gauge to it via a 3D process. We're looking at printing of closed-loop systems, so actually can we get a system to respond based upon the sensor reading. Doing a huge amount of UAV applications, so sensor layers and UAVs. Also 3D printing via UAVs, which is what this one is done here. And moving into things like nervous systems for objects. So can we incorporate sensors into objects and feed that back into the design loop almost when we're designing them. What else has been done? So we're not the only people working on this. Give you a kind of a realistic viewpoint. This, because we're in Orlando, is fairly relevant because this is the body of work that Disney did. So trying to use 3D printing to make sensors and interface devices. And they demonstrated things like interactive toys and all that kind of stuff. The other way to do it, I think this was actually printed structures backfilled with metals as well. Obviously making holders for existing hardware. Should be fairly familiar to one of our chairs. And then there's all sorts of things like Autodesk have done where they've actually 3D printed a knitted structure and incorporated sensors into it. So there's a huge amount going on in this field. It may not seem like it, but there is a huge amount of work going on. So it's proven interesting technology across a range of applications. Allows us to consider new ideas and new approaches. Can be used to feed back into the design process, but the important bit is it's not a cure-all for everything. If someone comes to me, the first thing I'll say is, can you make this via another process? It's not a cure-all, it's another tool in the toolbox. I'd just like to acknowledge my group there, also the Ultrasonics group in the engineering at Warwick, and some of the sponsors. Thank you very much.